Okay, today we are going to analyze a series circuit. That means when I give you the voltage and all the resistance or values of resistance for each resistor in the circuit, you're going to be able to tell me the current at any point in the circuit and the voltage at any point in the circuit. While you're doing this, you may find it helpful to refer to slide 17 in your electric current notes. This slide will remind you of how voltage, current, and resistance behave in a series circuit. So when we analyze a circuit, the first thing that we're going to do is determine the equivalent resistance. And when we say equivalent resistance, that means I can take out R1, R2, and R3, and I can replace them with just one resistor that's going to cause the circuit to behave in basically the same way. To do that, if you refer back to your notes, resistance adds in a series circuit. So the equivalent resistance is going to be equal to R1 plus R2 plus R3. In the case of this problem, it's going to be 200 plus 150 plus 250, which is going to add up to 600 ohms. So our total resistance is 600 ohms. And I'm going to fill it out. I've got a little table here that when I solve these problems, I like to fill out as a kind of a guide or a way to organize my answers. And you'll notice on the homework that I do the same thing for you, give you a table to fill out. So that's step one. Step two is to use Ohm's Law to calculate total current. So I'm going to re-sketch what I have just determined here is that my 3 resistors can be replaced by one resistor that has a resistance of 600 ohms, and my battery is still 6 volts. By Ohm's law, V equals IR. I know voltage and I know resistance. I can calculate current. So 6 volts is equal to I times 600 ohms. If I divide both sides by 600, the current is 0.01 amps. That's my total current. So I'm going to put that in here, 0.01 amps. And I can go ahead and put in the total voltage. It's always going to be the voltage on the battery, in this case 6 volts. Next, we are ready. Step 3 is carry back the constant variable. So it's going to be different for parallel versus series, but in series, the variable that's the same everywhere in the circuit is the current. So in this case, we're going to carry back the fact that current is 0.01 amps to everywhere else in the circuit. So through resistor 1, the current is 0.01 amps. Through resistor 2, the current is 0.01 amps. And through resistor 3, the current is, you guessed it, 0.01 amps. That happens because, again, the current is constant everywhere in a series circuit. Next, step 4. Step 4, you're going to determine the other variable. In this case, that other variable is voltage at all other points in the circuit using Ohm's law. Well, Ohm's law is still the same thing. V equals IR. And we're going to solve for voltage. So at every point here, we can calculate voltage by taking current times resistance. So for the first resistor, the current is 0.01, the resistance is 200 ohms, so I times R, 0.01 times 200. The voltage at that point is 2 volts. At the second resistor, the current is still 0.01, the resistance is 150 ohms, the voltage is 1.5 volts. And finally, at the third resistor, the current is 0.01, the resistance is 250 ohms, so the voltage is 2.5 volts. We're ready for the last step, which is our check to make sure we're correct. So in a series circuit, the current is constant everywhere, that means the voltage adds. And the voltage in this case should add up to, at each of the individual points, should add up to the total voltage in the whole circuit. In other words, the voltage at the battery. So in this case, the added variable is voltage. 2 plus 1.5 plus 2.5 does equal 6. So this step 5 is really like a check. Yes, we checked it off. The total voltage is 6. That matches the voltage of the battery, what it should be. So that means we probably did this question correctly.